we're talking about, again, is this concept of non-classical light, which we define as a quantum state of the field which is not representable as a classical statistical mixture of coherent states. Okay? And examples of phenomena which are kind of smoking guns of such states are states that exhibit sub-Poissonian fluctuations in photon number counts within a given time interval. The phenomenon of photon anti-bunching, where we see correlated photons in such a way that the probability for having photons arrive together, separated at time 0, is smaller than them arriving separately. Okay? Photon anti-bunching. And those two phenomena we described are associated with photon counting. They're associated with what we call the discrete variables that are associated with the quantum field. And what we're discussing now is a different kind of phenomenon that's associated with continuous variables, and that's the phenomenon of squeezing. And what we say that the field is squeezed if the quantum fluctuations in one of the quadratures of the field for some phase is smaller than the value associated with the vacuum. Okay? If that's true, we say the field is squeezed. And so in order to address that phenomenon, we were developing some formalism. We were reviewing that. So we defined the quadratures of the field. They are related to the quantized versions of the real and imaginary parts of the complex amplitude of the field. And those quadratures are kind of the equivalent, if these were a mechanical harmonic oscillator, of the position and momentum of that mechanical oscillator. And so these phasors are in phase space. So that's where the term phase space comes from. And we have an operator that acts to rotate the phasor. It's really just the free Hamiltonian harmonic oscillator. The number operator is the generator of rotations in phase space. And so we defined rotated quadratures as such, and they satisfy, for an arbitrary theta, the canonical commutation relation. And we have, in addition, the phase space displacement operator, which simultaneously displaces in position momentum. And that can be written in terms of either the real quadratures or the complex representation in terms of the complex amplitude, etc. Yep.
I just have kind of a simple question about different quadratures. But I guess, I mean, when we do, kind of regular quantum mechanics, just with, particles and stuff.
The mechanics, yeah.
Yeah, I mean, X and P have very different physical interpretations, in terms of position, momentum. And here, I mean, would it be fair to say that the only difference between the difference between the quadratures essentially always depends upon some sort of phase, like the phase of some reference oscillator or
yes,
something?
I think that's fair to say.
Okay.
So of course, for a mechanical oscillator, the same kind of algebra holds. If I had a free oscillator and it had a certain momentum, then after a certain amount of time, that momentum will be translated into a position.
Oh, yeah.
So position is, I mean, momentum is the generator of translations in position, and position is the generator of translations in momentum. And that is true here as well. I mean, it's true that by sort of scaling out the variable, you know, there's no sort of units difference between position momentum.
Yeah.
Here. So they don't have a kind of distinct physical distinction the way position momentum do
Okay.
for a mechanical oscillator. But nonetheless, you know, they satisfy the same kind of, you know, translation generations that we do for mechanical oscillators. And, you know, moreover, it's for given a signal that oscillates, the two quadratures as we've discussed, if I had a, you know, a classical signal that was a function of time that had, you know, some amount of cosine and some amount of sine, these variables can't be specified with with perfect resolution quantum mechanically. They're incompatible observables.
Okay.
Yeah.
I was just going to say that for a mechanical system, you can define an x and a p that are like dimensionless.
Sure, we could.
By
Yeah.
the way I learned quantum mechanics,
Indeed.
my lecturer defined everything as like dimensionless.
You had a good lecturer. That's how it should be done.
But then I think you can do all this stuff.
Sure, sure. I mean, it's just a question of, I think Jacob's question is how should I mean, position momentum, we kind of understand what they have, they're sort of different physical concepts mechanically. But here, there's kind of no physical distinction between these two.
Maybe there isn't one mechanically either.
Did you just say, I'm trying to remember,
Yeah.
go all the way back in group theory. Did you just say that the momentum operator, or the position operator is the generator of boost?
Of a momentum translation, so yeah, I guess a Galilean boost.
Galilean boost?
Yeah. Yeah, I think that's fair. Okay, so now so we have our phase space displacement. If we had just displaced the vacuum state, we have our coherent state. And now we're talking about other kinds of states. So the vacuum state is this state that we write in phase space, looks like this. And if we think about this as a whole bunch of statistical mixture of different kind of classical phasors, then as a function of time, as this is rotating around at frequency omega, what we'll see is sampling from this distribution some kind of Gaussian noise with a spread here that's given by the vacuum fluctuations. And in these dimensionless units, this has a spread of a half invariance, square root of 2 in RMS. If we had something which we would call squeezed vacuum, then what one would find is that the as a function of time, if we were to sample it, the spread that we would see, the noise that we would see, would be different at different times. And we would see this kind of, you know, I'll see if I can find some of the data that sort of shows this, where you see the noise on the photodetector, if you were to take many shots over and over again, and then look at the distribution, the histogram you would see of possible values on your photodetector would be narrower here than here. Okay? And that's related to the fact that I have this phase-dependent spread, depending on the phase of the oscillator. Okay? And this is again what we call squeezed vacuum. So let's talk about then what is this quantum state? How do we represent this quantum state algebraically? let us define the following operator, which is often called the squeezing operator. And that operator is defined as the following. That operator is e to the r over 2, the annihilation operator squared minus the creation operator squared. That is a unitary operator because the operator in the exponent is anti-Hermitian, right? It's equal to minus its adjoint. So it's like I times the Hamiltonian. I'll get to the question of what the Hamiltonian is and how you make such a state. In a moment, we're just going to do a little bit of bosonium algebra. Okay? So let's see. So now this is a unitary operator. What is the unitary transformation that this state, that this operator, how does it transform the annihilation operator? Okay. Again, to do that, we make use of the, I guess, the Baker-Campbell-Hausdorff. I forget if that's this is actually Baker-Campbell-Hausdorff or not. I never remember which one that is. But you recall that either the A on some A plus the commutator of A with A plus a half plus dot 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 n factorial n times commuting. Right? So in our case, if this is S dagger on the left, and when you dagger it, you get minus this, what's in the numerator here is minus A. Okay, so when you dagger it, you get plus A in the numerator, and then it looks like the Baker-Hausdorff thingamaboozit. So that then is, let's look at the commutator of minus A, which is A dagger squared minus A squared times R over 2 commuted with the annihilation operator. Okay. So let me make sure I got all my signs right. That looks good. So that's equal to minus R A dagger. Okay, so this is equal to my big A with A. So now if we commute it again, second time, well, I'm going to get minus R out here, and then the commutator of A with A dagger. Okay? And that is equal to minus R times plus R A. Let's see if I do that right. Minus, yes, minus. So that's R squared A. And then I go back again, and it just keeps flipping back and forth between A dagger and A dagger and A. So the answer to the question here then is the following. This is equal to the sum over n even r to the n over n factorial a plus the sum over n I, oh, I'm sorry, minus, every time I pick up that extra minus sign from over here, r to the n over n factorial a dagger. And so this transformation, this unitary transformation, has the following form. S dagger r on the annihilation operator S is equal to the hyperbolic cosine as a function of this parameter r, which is called the squeezing parameter on the annihilation operator, minus the hyperbolic sine on a dagger. And this is an important transformation in this algebraic land that we're living in right now. And this has a somewhat familiar form to perhaps some of you who come from the world of low temperature physics and bosons and condensation and so forth. This is known as, and it's known in the quantum optics literature now, as the Bogoliubov transformation. So it was first introduced in the context of elementary excitations elementary excitations of a boson sign condensate, but we'll see how that connects in any way to what we're talking about now. There's a slight connection. But anyway, this is what's called the squeezing transformation. Why would this possibly be called the squeezing transformation? Well, let's look at how this Bogoliubov transformation transforms the quadratures. So let's look at S acting on doing the unitary transformation on the X quadrature. Okay? Just to simplify life a little bit, instead of writing cosh r and sinh r, I'm going to write script C and script S. Please don't learn how to write cursive anymore, but that's what I heard. It's kind of, anyway, I'll be an old fart. I'm going to be an old fart tomorrow. It's my birthday, so I can complain. That's a cursive C and cursive S. Anyway, right, so let's write this out. This is equal to, this on A plus A dagger over root 2. Okay, so this is then equal to cosh A minus sinh A dagger plus cosh A dagger minus sinh A over root 2. Right? And so that is equal to cosh minus sinh over root 2 A plus yeah, that's what it equals. Cosh minus sinh A plus A dagger over 2. Right? And what is cosh minus sinh? Well, cosh is e to the r plus e to the minus r over 2, and sinh is e to the r minus e to the minus r over 2. So cosh minus sinh is e to the minus r times x. So the Vogel-Lyubov transformation on the x shrinks x by this amount. And you go through the algebra and you will find, as you must, because the commutator is conserved under a unitary transformation, that this goes to e to the plus r. Okay? So that the commutator of this with this is as before I. So, with that said, we define the state, the squeezed vacuum of the sort that's sketched over there on that board, as you take, so the squeezed vacuum with parameter r as what you get when you apply the squeezing operator to the vacuum. Okay? So, what are the properties of this state? So R is defined as the squeezing parameter. Firstly, what are the expected values, the mean values of the quadratures in this state? How would we know? Well, we could, if I use the definition, this is equal to S dagger. So I can think about it in kind of Heisenbergian picture, where I now transform the operator rather than the state. And this is equal to e to the minus r times the vacuum expectation value of x, which is 0. And similarly, the expected value of p is, and therefore any quadrature will have expected value. That's the vacuumy part of the squeezed vacuum. But the squeezy part is about the fluctuations. So if I want to know what is the, say, what is the expected value of the variance of the quadrature x in this particular state, that is, of course, the expected value of x squared minus the square of the expected value of x. This is 0, as we just described. And this, again, doing the same trick of moving the unitary operator off of the state and onto the operator, and using the fact that it's unitary so that we can bring the unitary operator inside any exponent. This is equal to the vacuum expectation value of the squeezed x all squared. And that is equal to either the minus 2r times the vacuum expectation value of x squared. And the vacuum expectation of x squared is a half.
Yeah.
So this is e to the minus 2r. 2. So the RMS is that. And similarly, for this particular state, the P quadrature is anti-squeezed. It's expanded by this amount. So the parameter R in the squeezing operation tells me the exponential, by what exponential amount. Typically, we'll talk about T, because some noise engineer decided everything needs to be discussed in base 10 and they're written in decibels. So we always talk about so many dB of squeezing. So we somehow have to change from R to base 10, but we'll get anyway. All right. So this is the Boliubov transformation. This is for that particular squeezing. Right. Okay. Good. So yeah, that's an interesting point. So first thing, this is called squeeze vacuum, but it's got photons in it. Okay. So this is not your father's vacuum. Mother's, I don't know whose vacuum it is. But anyway, let's take a look at this state. So this is equal to either like R. And this state, if R is small, which, typically it is unless you look really hard, then this is approximately just a slight displacement from the identity, your identity transformation. On that.
Square on your thing.
Yes, thank you. Of course, it doesn't matter because this acting on the vacuum does nothing. And so this is approximately equal to the vacuum and then some amount of 2 photons. Okay? The amount of 2 photons. And this fact that we have a coherent superposition of the vacuum with some other number of photons is why this is a phase-dependent phenomenon. Remember, we have this phase number uncertainty relation, right? If you have a state with a definite number of photons, then it has no phase at all, complete uncertainty in phase. So this coherence is sort of what's associated with the continuous variable nature of this thing, the fact that there is a superposition of vacuum. And it's the destructive interference that arises from these 2 possibilities that is what gives rise to the fact that this fluctuation is less than 2. We can look at, if we take this as our approximate squeeze state, we can look specifically at what happens to say, so this is, if this is approximately the state, we can look again at what we just calculated. Let me write it over here. This is still 0, right, for that state. So let's look at this. You notice that, I mean, if I had something with one photon, a superposition of 0 and 1, the expectation value of x would not be 0, right? Because this creates or annihilates one photon. So there's off-diagonal elements associated with 0 and 1 for x. That's a displaced state. The displacement operator has 1 power of A for A dagger. But this has got 2 powers. Okay, so let's look at this guy. So that's equal to approximately, well, let's write it out. This is equal to A squared plus A dagger squared plus A dagger plus A dagger all over 2. Okay, and now if we plug in this approximate form of the thing, what do we see? So, right, this is equal to 0 minus r over 2 times 2. That's a state with 2 photons. Okay, plugging that in for our squeeze state. Yeah.
And wouldn't I don't know, when we apply the annihilation or the creation operator twice, wouldn't we get some other square root?
Oh yeah, we
something?
do.
Yeah.
Yeah, we do. So there's this is over square root 2.
Yeah.
Yeah. Yeah. Thanks. Yeah, we got that. I think that's actually right in the notes. Double check that. Yeah, it's right in the notes. That's good. Right. So you do this out, and what you get is 1 minus r over 2. You know, this is the approximately u minus r over 2 for r small. So it's that destructive interference between these alternatives that's giving rise to this squeezing effect. But this state does have photons, and in fact, the mean number of photons in this thing, if you were to look at A dagger A, is equal to the hyperbolic sine of R squared. Okay. So that's a particular squeeze state of this sort. We said more generally we could have squeezing along an arbitrary quadrature. So we need to have something a little bit more general. So let's say we have a state which is squeezed along some other quadrature. Say the quadrature here defined by that angle theta. Okay? So I'm going to have a squeezed vacuum which is squeezed along that quadrature. Well, we know how to create that state using the algebraic tools that we've developed. This is just a rotated version of the squeezed vacuum that we had here, right? So this state, which we'll call, for reasons that will become clear in a moment, and everyone likes to draw a zeta if you have a chance. 0, it's not C, the other squiggle. This one has only one squiggle, it's a zeta. This is the rotation operator acting on the squeezed vacuum. Okay? So from that we can define, stick in an R dagger R. Do that. This leaves the vacuum unchanged. And this I'm going to call S as a function of zeta acting on vacuum. What is that? So S as a function of zeta is equal to excuse me. I just realized I did one thing backwards. The way we've defined the rotation operator rotates things counterclockwise. This is the rotation clockwise. To double check that. Yeah, the way I define R. So this has to be R dagger. Because we've defined it e to the minus I theta. Yeah, I was wondering where that was going to come from, but now I see why. Okay, so we're good. This is what we got. And this is equal to the rotation operator e to the r over 2 a dagger squared minus a squared, or a squared minus a dagger squared, the rotation. And then we shove that in the numerator, in the exponent, as we've done many times now, and that becomes e to the and I have to check my signs on this because it's backwards. But anyway, it's basically correct. There's some sign nonsense that I don't see what I did wrong with. So this is equal to 1/2 zeta star a squared minus zeta a dagger squared. Where zeta, oh no, it's good, it's right, is r e to the 2 pi theta. So this is known as the generalized, this is the general squeezing operator. And it squeezes, it's got a squeezing parameter that is a complex number. The magnitude of zeta determines the degree of squeezing, and the argument of it determines the quadrature along which you're squeezed with a factor of 2 in there. So if the zeta parameter is real, you squeeze along the x quadrature. If zeta is pure imaginary, then you squeeze along the p quadrature. All right, so we got what we need in terms of the algebra here. To finish this piece of the algebra, we need to write down what the general Bogoliubov transformation is. So if you go through the same procedure with the Baker-Campbell-Hausdorff as we did a moment ago, what you get is the following. Okay? And this is the general view of conservation. So, if I were to now ask, what is the fluctuation in a quadrature along some phase phi given a state specified by squeezing parameter zeta? You do that algebra, you get the following. You get e to the minus e to the minus r times cosine squared theta minus phi plus e to the plus r over 2 sine squared, where zeta is r e to the 2i theta. So when your phase quadrature is aligned with the direction of squeezing, you get this amount of squeezing. When it's aligned at 90 degrees relative to that, you get the anti-squeezing. Yeah?
Are there supposed to be 2 R's instead of R's? Because I thought that was what we had in the regular squeezing case. Because when
Oh,
you
you mean the variance?
Yeah, yeah.
Yes, indeed. It's e to the minus 2r. Indeed, this is squared. Thanks.
Cool.
Yeah. Thanks. So, if I were to plot this variable as a function of the phase quadrature in which I'm looking, what I would find is the following. I would find that it would oscillate depending on the value of theta. So it looks something like this. Okay, where this level is a half, and the minimum value is e to the minus 2r over 2, and the maximum value is e to the plus r over 2, and this level is the vacuum level. So, in order to see squeezing, we're going to discuss now how you see this, one needs to somehow measure these fluctuations as a function of the phase quadrature. And what one should see, if it were vacuum, you'd have the same variance at no matter what sort of time you're looking at it. Whereas here you see these different values, and you would see that if there was nothing, if I were just measuring the vacuum, however we do that, we can discuss that in a moment, we would see this level that would calibrate us, the vacuum level. And then we have to measure something as a function of some parameter that allows us to measure these quadratures, and we would see this thing dip below the vacuum level. And that would be squeezing. All right? So, how in the world do we measure such objects, such observables? Well, this has something to do with a phase. So we really want to do some kind of interference experiment. We need to reference, I mean, it was kind of your question, we need to reference what we're measuring to some phase. So in order to do that, have what's called phase-sensitive detection. So the idea is, instead of just, having a photodetector detect our signal, we're going to do the following thing. Here's the signal, the thing we want to measure. What we're going to do is look at an interference between the signal and what is known from the vestiges of radio engineering as the local oscillator. Okay? So you have some well-defined oscillator. In the context of optics, this is a laser. Okay? And this is what's called the local oscillator. And we're going to put this on some kind of beam splitter such that we look at the beat note. Between the signal and the local oscillator. Right. Now, typically, just from jargon perspective, our signals that we typically are considering are monochromatic or quasi-monochromatic, narrow band fields that are specified by some frequency omega. Okay, and the local oscillator has some frequency omega sub L. Okay, and some well-defined phase. Now, if omega equals omega L, and then we detect this, by the way, on some photodetector. Then we call such a scheme, because they're the same, as homodyne detection. And if omega is not equal to omega L, then we call it heterodyne. Okay. Of course, if you have omega not equal to omega L, then the beat note's going to have some difference frequencies, and there's going to be and there's other information. We'll come back to heterodyne at a later date. For now, let's talk about homodyne detection. Okay, so let's look at this firstly classically. Okay, so let's consider the case we have. So now these guys are going to be the same, but this is the same. I'm not going to mention the frequency. Everything is at the same frequency. Homodyne. And we have, this is specified by some complex amplitude E, whose magnitude is the square root of the intensity and whose argument is the phase of the oscillator. Okay? And then we have the signal, I think this. Okay? And then we have the out amplitude. So my complex amplitude out is the transmitted part of with the transmission coefficient T of the signal and the reflected local oscillator. Okay. Now, if I do this, and this is what's known as, the way I've drawn this is known as ordinary homodyne detection. We'll explain what is not ordinary in a moment. But this is what's known as ordinary homodyne detection. So now, if I look at, say, what is the intensity of the output field, well, that's the square of the amplitude up to some factors that we never keep track of. And that's going to be equal to the transmission coefficient squared times in plus the reflection coefficient times that plus the cross terms. that's equal to T R star E in E L star plus T star R E in star. Yep. So this is equal to the transmitted intensity plus the reflected intensity of the local oscillator plus the square root of T times R times the intensity of the local oscillator times E in e to the I, the phase of the transmission coefficient minus the phase of the reflection coefficient plus E in star e to the minus I, the difference in those phases. Okay, well, we sort of see emerging here something that has to do with a quadrature of the field rather than just the intensity. Firstly, if I have a symmetric beam splitter, as we discussed last semester, for symmetric beam splitter, the argument, the phase of the transmission, we can take, for example, T to be equal to the square root of T and R to be equal to 1 minus the square root of T times I. That's for a symmetric beam splitter. It doesn't have to be that way, and you'll see this in many of the quantum optics texts. Sometimes you'll see that there's a difference in sign depending upon whether you reflect from one side of the beam splitter compared to the other. That's like if you take, I guess if you take a piece of glass and you coat it with a little bit of metal on top, that would be a different beam splitter than something which is, you know, say just a piece of glass. It's not symmetric on both sides. All right, so what can we say about this detection scheme? Well, so I'm going to replace this by let's just do this over here. This is, oh, I forgot about the phase of the local oscillator. That's important. I left that out. I'm sorry. I had the phases of the transmission, but I forgot about the phase. That was truly the most important phase that I forgot to write down. This pi over 2 is coming from the difference in the reflection and transmission phase. But this is truly important that from that, because E sub L was equal to the square root of the intensity times the phase. Okay, so this output intensity, right, it's the transmitted in part plus the reflected local oscillator plus the square root of T R intensity times, and then I'll put a factor of 2 in there, X. Where X is the classical quadrature at the phase of the local oscillator plus pi over 2. It's that phase quadrature. E to the L, e to the minus I. This should have been minus, this plus, because that was an E star. plus E in star given I by L over root 2. So there is a component of this output signal that is the beating between the input signal and the local oscillator. And that beat note is the quadrature along a particular phase that depends on the phase of the local oscillator. Now, typically, what we're interested in when we're doing homodyne detection is the situation where we want to measure the signal, right? So we don't want to reflect most of it. We want this to be highly transmitting, right? And just a tiny bit of reflection. So in an ordinary homodyne detector, the transmission coefficient for the intensity is soon to be huge compared to reflection. So they don't, I transmit most of the intensity. However, one cranks this up, one wants to measure this ultimately. So one typically, in this case, makes the local oscillator very, very high intensity, you know, in an ordinary homodyne detection. One cranks up the intensity on the local oscillator, okay? In such a way that even though this is true, we'll have R times IL to be much, much bigger than T times input intensity. So that this is small. Okay, so with that said, let's look now at the noise. So this is the amount what you would see the signal, but what we're actually interested in is the fluctuations. Okay, so let's again just think about this classically for a moment. The fluctuations in the intensity. Well, that's going to be R squared times the fluctuations in the local oscillator that are reflected. And then we have something which is T times R times IL times twice the fluctuation in that quadrature. Now, if this were a coherent state, a stable laser, this fluctuation intensity would be on the order of the intensity, right? Because the fluctuations in N are N. And since T is huge compared to R, and this is I, this is negligible compared to this because of this approximation. So under those conditions that I had a very good local oscillator with no more excess noise than the standard, then my noise is dominated by this. And thus, I measure what I want to measure, which is the fluctuations in that quadrature. So that's the way in which we can measure the fluctuation of the quadrature is to beat this thing we want to measure with a local oscillator that has a well-defined phase, and then the beat between them allows us to measure a particular quadrature, and if we designed it all right, the noise is dominated by the noise in that quadrature. Yes?
So you have a input laser intensity that's much stronger than your input intensity, but you also have a
mirror that is
allows through much more than it.
Yes, that's correct. Both things are important for ordinary homodyne detection. Now, this is not the best way to measure quantum noise. The reason is that if there's any other noise on your laser that's beyond perfect shot noise, then you're going to corrupt this tiny amount of squeezing that you have with reflected noise from your laser. And so this is not typically the strategy that is used. At least I don't think so. Instead, we go to something which somehow gets rid of any noise, any fluctuations that are coming from the local oscillator, and only measures the fluctuations associated with the signal that you're interested in. And in order to do that, we have to break out our wallets and buy another detector. So we have two detectors now. And we now look at the difference in the intensity between these two photodetectors. And instead of having that beam splitter that was very, very highly transmitting, this is now a 50-50 beam splitter. This scheme, which we will now analyze, is known as balanced homodyne detection. Okay, so let me think about a few things here. Right. Okay. So I just want to get my notation in here. Let's call this E1 out and this E2 out. Those two fields that are on these two output ports of my 50-50 beam splitter. So again, I'll take it to be a symmetric beam splitter and 50-50. So that means that E1 out is my signal 1 over root 2 for this times the signal plus I times the local oscillator. Okay? Transmission is 1 over root 2. Reflection is I over root 2. And my E2 out is 1 over root 2 E local oscillator plus I signal. Transmission of local oscillator, reflection of the signal. And what I look at, the thing I care about is the difference in the intensity of these two guys. So I square those amplitudes, I do it all out, and voila. What I get, and this looks like, yeah, those notes are not right. What I get is the square root of 2 times x. I've got single phase squared. So a balanced homodyne detection, I mean, you can kind of see that, right? You square this, you're going to get intensity 1 and intensity of that guy. Square that, you get the 2 intensities. You subtract it, you get rid of the 2 intensities. What's left are the cross terms, which have opposite signs. And so you end up solely with the interference term. So a balanced homodyne detector gets rid of anything that has to do with the noise in the local oscillator and just directly measures the quadrature of interest. So in most experiments in quantum optics where you do homodyne detection, I believe it's the case that it's advantageous to do balanced homodyne detection. Although I vaguely remember reading a paper where it talked about why actually no, you really want to do ordinary homodyne. And I tried to find the damn paper, but I couldn't. And all the textbooks always say this. So anyway, if someone knows someday, tell me. Before I write that. All right, class. Okay, so now we discussed this classically, right? What we're really interested in is the quantum aspect of this noise. So we want to look at this from the quantum perspective. So in order to do that, let's just remind ourselves about the aspects of quantum noise in photodetection. All right. So what we discussed last semester is that if I have an ideal photodetector, a photodetector that has unit quantum efficiency. So what I mean by that is the following. So the jargon we use is unit quantum efficiency. What that means is that if a single photon hits my photodetector definitely goes click with 100% probability. There is no such detector, but they're getting better. Okay? Now, if I had such an ideal photodetector, then if I do a measurement of and count photons, and I do the experiment over and over again with the same state of light, and I don't see the same number of photons, then those fluctuations are due to the fact that I had an uncertain number of photons coming into the detector. And that's known as shot noise. So there's other kind of contributions to shot noise which might have to do with the photodetection process itself if I don't have an ideal photodetector. But if I did have an ideal photodetector and I don't see definite photodetection, number of photons, then that's due to shot noise. So shot noise, as it's called, in photodetection, had a fundamental contribution due to the fluctuation in the photon number of the quantum field. So for example, if we had a coherent state, we have a laser that we shoot on our photodetector, and if we had this ideal unit quantum efficiency photon detector, in that case, what we would see is Poisson number fluctuations. So for a coherent state, the fluctuation in the photon number is equal to the mean photon number, right? Poisson. Now, of course, n is measured relative to some amount of integration time that we're counting. If n is small, then if I do this experiment here, what one would find, is we'd kind of be in Geiger mode, where we would count individual photons. So we would see a photon in a gate interval, and then maybe none, and then we see another one. We'd see, you know, fluctuations like this, Poisson statistics. On the other hand, if I had n big compared to 1, then I'm not going to just see these discrete counts. I'm going to see something more like a continuous current. And if I had this coherent state here, so here alpha is small compared to 1, here alpha is big compared to 1, and I looked at this, what I would see is something more like this as a function of time. You know, I'd see some average intensity, but I'd see some noise. Around that mean. And this is my photocurrent function of time, would be the shot noise. Now, where is that shot noise coming from? Again, it's coming from the same fact that I don't have a definite number of photons coming in any interval. So the photocurrent that comes on my detector won't be this average value. It's going to fluctuate. But it has a kind of different character here than this kind of counting system. Now, one way to look at that is the following. This, if I looked at the number operator, that's equal to A dagger A, right? Which we're saying as fluctuations. If I make the Malo transformation that we discussed last semester, so I'm going to transform away the mean value, alpha, and so I'm going to define B as the displaced version, and the state displaced back to the origin. If I do that, so this is equal to, oh, I'm sorry, the other way around. This guy is displaced minus a dagger. So then that means that my operator is alpha plus B. This is the mean field. And this is the fluctuations around the mean. Then if I look at what A dagger A is in this case, well, that's going to be equal to alpha squared plus alpha star B plus alpha B dagger plus B dagger B. And if I've done this transformation, the mean number here, this is 0 on average. So this guy has no contribution. What I see is that my signal, my average signal, number of photons that I see here, is equal to alpha squared plus alpha e to the minus IB, if it's B, plus e to the I by B dagger. So what do we see here? What we see is that the photon number here is the mean photon number plus fluctuations about the mean. And those fluctuations about that mean depend upon, this is the amplitude quadrature. In other words, if I do direct photon detection of a coherent state, then what I'm going to be measuring is the mean value and fluctuations about the mean along the direction of the phase. And if this is not a coherent state, if it's some other state with some other, I'm still measuring those fluctuations. This kind of distribution, of course, this, what we would call, this is more the continuous variable picture. And the shot noise that we see around the mean is Gaussian. Because the limit of a Poisson distribution for large average value is Gaussian. So what we're going to discuss on Thursday is how through balanced homodyne detection we can see reduced fluctuations and therefore measure squeezing. Notice it was kind of thrown out pretty quickly in this last 5 minutes. We'll review this part again on Thursday. All right?